number for a given row, so it gives these two densities. Okay, and again you see that, okay, see binodal curve, you derive whatever you can derive theoretically that matches extremely well with a simulation of the microscopic model. Okay, and then you can see that you can in fact look at the distribution of the densities within the microscopic model, and you see that, okay, as you expect that this is a separated space, so you have this whatever the by one density. Okay. Third line, yes, I am going to come to the third line. Okay, so there is a third line. So I'll just come back to the third line. This thing. Okay, so now in fact you can see that, okay, if I just take the so in the previous one I was showing that, okay, the microscopic and the macroscopic matches this thing, but in fact you can actually see this, so this student has made a nice movie, so I think somehow okay. Okay, so it's supposed to work, but I don't know how it. Okay. Okay, so this is this. Okay, it's working something. Okay, so yeah, so you see that actually if you start with something profile and then finally this goes to this separated. So this is this outside this binodal where it goes to the homogeneous state, and this is inside this pinodal which goes to this phase separated state, and these lines are basically the evolution of the hydrodynamic equation, noiseless hydrodynamic equation, and these points are basically the molecular this simulation of the microscopic model, and they follow nicely. Okay. So you can also compute the 2-point correlation function for this model, and so for the 2-point correlation function starting with this fluctuating hydrodynamics, basically you compute these 2-point correlations between density or density whatever polarization or polarization. Okay, so this, okay, I have not given you the analytical expression, but you can actually find this in the homogeneous regime, you can find this expression exactly. Okay. And so and then, okay, this basically has this exponential decays. Okay. Okay, so higher dimensions, so this model you can actually straightforwardly extend to higher dimensions. So there are of course multiple ways you can actually extend to higher dimension. One way is, of course, you can just take that number of lane to be very large and you just keep the same dynamics basically, and this lane crossing time basically now you take it to be this one, so it's basically with the same as the diffusion time scale, this thing basically. Okay, and then in this case again the noiseless hydrodynamics what you derive is basically the same as the 1D hydrodynamics equation I have derived basically. Okay, so if you just take the lane to be large, so then because it's essentially active in one direction, so you get the same noiseless hydrodynamics. But you can also have a isotropic generalization basically where instead of this lane crossing, okay, you have a lattice, and then okay. So there are now 2D species, and basically that defines these various directions, and each species has a favorite direction to move to, so that goes with this rate, and then in the rest of the direction it goes with a lower rate, and then one species can tumble to any of these species basically with a rate this one. Okay, so in this case also you can actually follow the same thing and derive this hydrodynamic equation. So this hydrodynamic equation is okay, it's slightly different. Okay, but you can.
I have a stupider question actually.
Yeah.
Which is how do you even get any binodals or spinodal from the Monte Carlo simulation in 1D? Because you don't have a phase transition in 1D, I would think.
It's quasi 1D. So that's why it's very important, quasi 1D. Right? Yeah. Yeah. Okay. So now, of course, both this kind of model, you can see that okay, you start with something and then it separates. So this is this where you take the lane to large, and then okay. You see that okay, this is basically given by this 1D hydrodynamics, this thing, and there okay, you have another hydrodynamics equation. Okay, so in fact, I think you can see basically if you start with some this state, and then finally it basically goes to this phase separated state. Okay, yeah. So this is a advantage of working with students because they like generating these nice pictures basically. Yes. Okay, so how do you derive this hydrodynamics? So it's not possible for me to actually go to the whole derivation, but let me just give you a sketch. So as I say, so initially you describe in terms of these occupation variables. Okay, so these are this n. Okay, and now you write down what is this propagator, or it says basically starting with some n0. So these are this these are these vectors basically initial occupation, how do you go to this final nt at some time t? Okay, so this again is basically the vector for the whole system. Okay, so these are the occupation variable. So this you can basically write down this given this microscopic rule. So you can write down this formally you can basically express in terms of some action basically. Okay, so then you go to this continuous variable, and then so these are this hydrodynamic variable, and then from there, okay, you can either write a rho plus rho minus, or you can write in terms of rho and m. Okay, and when you go through this one, so what you find is that okay, you will have some action like that with something like that, where Hamiltonian okay will be given something like that. Okay, so don't worry about okay the exact expression of the Hamiltonian, but basically you start with the microscopic, and then okay you have an assumption of okay local equilibrium this thing, and then okay you just go through this. So these are this procedure people have earlier used for this other processes basically. Yeah, there's a question somewhere? No. Yeah.
In the previous slide, why do we have this voids in this MIPS in the right side?
That's a good question, and in fact you get it, and apparently I was told that even in some simulations or experimental systems apparently you see this void. So, but see this whatever the your binodal or this whatever this thing, they do not exclude. It just says that you have a two regions, one is a high density region and you have a low density region. It does not say that you can have void or you cannot have void, but apparently there are systems where you have seen this kind of structures actually.
No, but that depends on, so when you eliminate the m, right, and write an equation for just the rho, is the rho dynamics AMB or AMB plus? Because you have
see, this is just microscopic evolution. You just take the microscopic model and what it gives, whatever it gives, right? So now is a question of if you want to write down the hydrodynamics, it should reproduce this.
So in the continuum level,
yeah,
if you have AMB plus, not AMB,
yeah,
then you do expect voids.
Yeah.
And that's because you have microphase separation and not phase separation in that model. Whereas
no, these are not microphase separation. I'm going to come. This is not microphase separation. These voids are not micro. These are macro voids.
But these are bubbles, right? I mean,
these voids are not micro voids.
But
Yeah, yeah. Yeah. Huh?
the plus is an
This
extra.
is a simulation. Yeah.
It's an extra term in the equation of
Microscopic simulation, but this is at the macro scale.
I'm
but-
saying this is more like microphase separation.
Why do you call it as microphase separation?
A local gradient.
This is you are seeing at the macro scale.
No, AMB plus gives you.
You can
tells
have,
you that the
see, you can even have a,
is not a gradient.
see, nobody says that you can, the MIPS have to be one big cluster, no? I mean, you can have, I mean, this is what it gives, the simulation. Now, you can have or you cannot have means what? This is what, right?
Okay.
I mean, you do the simulation, you do the thing, this is what you get, right? I mean, now,
Let's just agree the system is not devoid of voids.
yes. Yes. So now, okay. Okay. So now, okay, given this whatever horrible Hamiltonian, so okay, so if you look at a Gaussian approximation in M, so okay, you have a slightly nicer looking Hamiltonian, and for this, okay, so these guys are this conserved current and this is this not conserved current, so you can basically, okay, this expression becomes nicer, and so in this case basically, so the corresponding hydrodynamics equations are basically given by this, okay. So in some sense, so if you start with this hydrodynamics equation and if you go through this Martin-Cizier formalism, so you end up with this action what I have just shown before, okay. So now let's come back to, yeah.
You went from the action to this?
Yeah, action, I mean, so given this action, the corresponding stochastic equations are these basically, right? Or if you start with this stochastic equation, you go to that action. Exactly, exactly. So these are unique mapping basically, either you go this way or the other way. Okay.
Sanjeev, 5 minutes.
Okay, I will be done, yes. So now why do I need the ladder, right? So in fact, if you take 1D model of this one, okay, and you just follow the same procedure, okay, you just naively follow the procedure, you end up with the same hydrodynamics equation, okay, okay. So So the knife following the procedure will give you the same hydrodynamic equation as this quasi 1D ladder, but it turns out that this hydrodynamic equation hydrodynamic evolution of the hydrodynamic equation, and you will evolve them together, and these are precise this thing because we know how to go from the micro parameter to the macro parameter exactly. So you do for this quasi 1D one, they micro and the hydrodynamics this thing they follow precisely. So it says that this no, it says that whatever the hydrodynamics equation you have written down, these are not valid hydrodynamics equation in one dimension. Okay, so that's what. So in fact, you can see if you take this hydrodynamic equation and fluctuating hydrodynamic equation, and then you compute the correlation functions of this density, they do not describe it. Okay, so in fact you can. So what is the reason for that? Okay, so what happens is that if you look at this quasi one dimensions, okay, so you see that actually there is a lot of activities going on, right? So this the system mixes, okay. So locally the system equilibrates. So it is, you can have basically this Bernoulli product measure locally. On the other hand, for this strictly 1D model, so these are what I call it microclusters basically. Okay, so particle aggregates, but they aggregate at the level of micro level, 2 particle, 3 particle, they will aggregate. And this one, because see, if you take this system in 1D, this flipping happens at a much slower rate, right? Going from plus to minus and minus, so that happens at a much slower rate. And at that time scale, the system cannot mix. That retains the order. If you have some 5 plus particle here, 6 minus particle here, some 3 plus particle, that order retains. So it actually the system cannot mix. Okay, and because it cannot mix, basically it does not have this. So magnetization, for example, or this M polarization, it cannot equilibrate basically. Okay, it's a conserved this thing for this, and that you can actually even see, like if you actually compute the density profile. Okay, so density profile is easy to compute because okay, given a global density rho, coarse-grained density rho, you can write down this whatever the box density, just a binomial distribution, and then if you take the Starling approximation, which gives you this, yes. So that's why you need this this thing. Okay, and this is in fact consistent because many other studies they have found that actually in one dimensions you cannot have MIPS basically, right? Yeah. So the reason you found this in Julia-Trier model because you had this exchange this thing and that this thing. Okay, so you see that okay this so at low Peclet number so this is in the homogeneous regime. So in the low Peclet number, of course, this hydrodynamics and this microscopic this thing, so they seem to describe because okay at low density it's almost like a low Peclet number, you can think of it like almost like equilibrium because particle just don't go and basically get stuck to each other. But if you take this high Peclet number, you see that actually your density profile what you get from the microscopic simulation and whatever your theory gives, they differ very much, as opposed to if you look at the quasi one dimension, it explains extremely well. Okay. So there is some little bit of discrepancy here, but this is because okay, so this is a finite size system and you assume that okay your MIPS is a clean MIPS basically, but then okay you have a boundary and okay in the boundary if you don't take care of it this thing. Okay, so to conclude basically okay, so we have proposed a minimal model of interacting particles with exclusive volume interaction and hardcore this thing condition. So for this model actually you can actually derive this hydrodynamics using a bottom-up approach, and this system exhibit MIPS.
Thank you for a beautiful talk. I want to check what is eta F. So you have introduced some quantity.
Yes.
Subscript F.
Yes.
I missed your explanation.
Yes. I think This one. I
Yeah,
guess,
for
right?
example, rust.
Yeah, yeah. So this noise is coming from because plus particle is switching from the plus going to minus and minus going to plus. So this basically the fluctuation of this m variable because of this switching.
Change of the variable.
Yeah. So there is a fluctuation because of this tumbling basically. Yes.
Tumbling
Yes.
noise.
Yes.
Okay, thank you.
Yes. Yeah. So in fact, it's basically a Poisson process, and okay, in the bulk, if you take the Poisson process, and then okay, this is just a Gaussian approximation of the Poisson process.
I'm intrigued by the beautiful agreement between your theory and the Monte Carlo simulation.
Yes.
Did you monitor the rectilinear diameter, how it vanishes when when you have the coexistence, so you have two branches. So when you look at the distance between, for a particular Peckley number, distance between two values, and how does it vanish when you go to the apex? Does it have a critical exponent?
Yes. Oh, sorry. So I think okay.
What is the value of that?
Yeah. So that is what. Okay, let me just come to that. That also reminds me this.
Yeah, there.
Question. Yeah. No. That also reminds me
Right,
this
but-
dashed line. Actually, I was supposed to explain.
Yeah, also I like to know whether there is a critical exponent to that one.
Yeah.
What is that?
Exactly. So now the point is that, okay, so as I said that this is the spinodal which says, okay, inside this system is linearly unstable, okay. This is binodal, it says that, okay, if I have two densities, basically it can, it separates, one density will be this and one density will be that. And in between this, it is a metastable region basically, in the sense that if in principle, if I take any density here, it can split into two densities. But that depends on whether you are starting with already a separated state or a homogeneous state. And I think if you use noise, basically it will finally go to the homogeneous state. And this dashed line is the one where this correlation functions what we computed from the linear stability, from the fluctuating hydrodynamics up to a linear order, that diverges at that line. Okay. So now near that line actually we don't have a very good description. Okay. So now to answer your question, we need to do more basically. So we don't have a very good handle as this closes there, because in that case, okay. So I think we need to, there are two things, okay, we probably need to go beyond this Gaussian noise, this thing. And the other thing is you have to basically solve probably the full hydrodynamic equation and not just, yeah. So we do not know what is the critical exponent around that actually, yeah. But maybe we can discuss if you have any idea.
Because I can understand from simulation, I know it's very difficult to do.
Yes.
But from your theory, you should be able to make a prediction of what that exponent could be.
But these are very nonlinear equations, so I don't know how, I mean, these are nonlinear equations.
I got it. You got to do renormalization.
Yeah, exactly. So that's something we have in the plate, but okay, it's like a long, yeah, okay, Satya.
Yeah, so, okay, I have a couple of questions. One thing is that, can you also develop something like Kawasaki-Dean equation for these kind of things, like what we do using interacting particle systems?
Yes.
For passive particles?
Yes.
Is there an active version of it? And does it sort of match with this kind of hydrodynamics?
Yes, we have not done it, but in principle it is possible, but you have to describe at the lattice level basically. It's not in the continuum. Going from continuum to hydrodynamic in this way is difficult, but going from the lattice, so if you define an equivalent lattice model with interaction, it should be possible basically to do that. Yeah, but we have not. We have not looked at it actually. Yes.
The other question is a general question that I understand is hydrodynamics, but usually, often, sometimes, when you you can ask, why does this equation close onto itself in two fields, rho and m? Because typically, like often when you go from lattice model to continuum model, 1-point function might include 2-point function, 2-point will involve 3-point.
Yeah, exactly.
This BPGQI hierarchy type of thing.
Exactly.
But here somehow rho and m
So,
closes onto itself.
yeah, because I think because of this dynamics, they
Fluctuations
locally equilibrate, and in this case, basically, it's kind of like a Bernoulli product measure locally, basically, yeah.
Right, so,
I mean, in the sense that if you just do a naive hydrodynamics, okay, this term, this usually comes from some Ni times 1 minus Nj, and then it's basically like a product measure locally. But that we do not do at the microscopic level, but we do it at the coarse grain level, basically.
no, but because if you look at the normal like symmetric exclusion process and so on, so there you can actually see that, you know, it does closes on.
Yeah, because it has a Bernoulli product measure, symmetric exclusion, basically, yes.
But then there's an underlying symmetry to the problem or something that makes it close.
Yeah, I mean, well, I mean, so.
I mean, here this model, see,
I mean, 2-point function might close on to 2-point itself.
yeah.
So 3 and 4-point may not. I mean,
So each species here is basically a WASEP, basically.
Sanjeev?
Yes.
What is the meaning of local equilibrium? I thought the systems are usually out of equilibrium.
No, in the sense that you can define this coarse grain density, right, locally, and within that you can, so okay, so if you just forget this guys for the time being noise.
For example, in a gas or something, when you assume local equilibrium, you assume a local equation of state.
Local temperature, let's say.
Local temperature.
Yes.
Connected to local pressure and local.
Yeah.
But here, what is the equivalent of that? That is the.
No, the measure for the profile, right? You can locally define a measure which is basically you can ask, okay, what is the, okay, so in the sense, what is the probability of having a plus particle there, okay? So that probability is basically rho plus locally, because, okay, that density you have defined in some range, and that's a slowly varying variable. So you can basically draw that Ni equal to +1 with rho plus and 0 with 1 minus rho plus, basically, right? Yes.
Does it, sorry, but does it work for generic systems or only after comparing with simulation you can check whether this approximation is, what is the,
So
how do I know it works?
so the thing is that if you have this whatever local equilibrium, so then it will work, but now a priori it is not very easy to see, because these are not rigorous mathematical derivations in the right. I have not rigorously proved that this system is has local product measure or something like that, right? So then in that case, okay, I mean, it's based on physical arguments, basically, okay, in one case, okay, the argument is basically that, okay, you have these two species, both are like this WASEP moving in opposite direction, right? And if you did not have this, so WASEP is basically weakly asymmetric exclusion process, but if you didn't have this flipping going plus to minus, they're stuck actually, the system, right? And this order cannot change, okay? So therefore, this doesn't have this local whatever equilibrium in some sense, right? Although each species has a Bernoulli product measure, but this will not have basically. Yeah. So I think in that vaguely, yeah.
Yeah, I guess I'm sort of, again, so the mathematical technique from coming from that, the action, where are you assume, is there an assumption of local, that's where I'm sort of.
Yeah, so this is basically, yeah, so this is.
Something that then fails in the 1D.
Yeah,
right?
yeah, so this is basically you do while going from here to here. So you have this microscopic this thing, and then from there basically you are describing in terms of a coarse grain density, right? So at this stage basically, yeah.
Okay.
Yeah. So usually, okay, so when you go from this micro to this macro, okay, there is also a, whatever this entropy term, but here, okay, entropy term is not very relevant this thing, okay, it's a subleading this thing. But basically at this level you have this thing, okay. But you can blindly follow these ones, okay, if you can just blindly write it down, okay, and then you will arrive at the same equation. That's what actually initially we did. We just take the 1D model and then, okay, you arrive at this equation. And then you see that actually it does not describe this
Yeah, but I guess as The question is, do you know where it fits?
Yeah, it's just
in the
basically from
process?
this microscopic axon to when you go to this macroscopic axon, this is basically at this scale, basically. Yes. Yeah.
If there are no further questions.
That's
So, first question, which is that, you know, the fact that you don't have phase separation in 1D is not a surprise, right?
It is not a surprise.
In the sense that even icing model in 1D,
Yeah, I mean,
phase transition, but if you write on model A, you would think that you have.
yeah, it's not a surprise, yes.
And as for Muthu's question about, you know, the exponents, you can indeed do an RG calculation with those nonlinearities in AMB or AMB plus. I think I've forgotten the upper critical dimension, but it's fairly low. So in any reasonable dimension, it's the equilibrium model B exponents. So Z is 3. The chi is half and Z is 3.
Yeah, so here, okay, at this stage, basically our first aim was to, can you go from this micro to a macro description, and which is, okay, usually like there are very few examples, because either you write down this hydrodynamics or you write down this microscopic model, but there is no connection usually, like, okay, you just, okay, appeal to some symmetry and cause. Yeah, exactly. Yeah, exactly. So, no, in fact, people often get that noise term wrong because, yeah, I mean, because this noise term is in fact quite, yeah, if you see this, yeah, I mean, not here, somewhere there, I had this one. Yeah, these guys. This is quite non-trivial basically. Yeah, you cannot just guess it basically, this thing, right? I mean, yes. Yeah.
Any further questions, comments?
Yes, John.
So if you do the Doppelity calculation, would you not get what the noise should look like?
This is what similar to Doppelity, but okay, whatever you call it. This is basically similar procedure. Right.
Yeah, but when you get the action, like, wouldn't you get the...
No. The question is, if you write down the phenomenological hydrodynamic equation, right, which is most based on some symmetry and conservation laws, we don't have any way to, I mean, guess what is the noise, this thing basically, right? So therefore, you need to go through this microscopic or axon formalism, whatever this thing, and that gives you the this thing. Right? Yeah. Yes. Yeah, equilibrium is easy because, yeah, I mean, because they are, yeah, exactly. Yes.
Any further comments? Okay, if not, let's thank
Okay,
Sanjeev.
thank you.
So he cheated. He started 5 minutes before his time and he ended 10 minutes after. So